Okay, so what I'm going to do first is share the review document right here. There we go. That's the review document with the review document key, actually. And I've got some selected, and I may pick out some extras as we go, but I do want to hit these for sure. Let me see. Yeah, this will be okay. We'll start with this one. Okay. So number one, so you're given a gas that absorbs 0 joules of heat, but it performs 30.7 joules of work. So the change in Q is 0 joules, and the work is 30.7 joules of work performed on its environment, on the surroundings, which means it has to be a negative number. Everything is referenced to the system. So this would be negative 30.7 joules. Okay. What's the change in internal energy of this gas? So remember, the change in energy is equal to the sum of the heat flow, the heat change, plus work. So it's really simple. You just add them together. So that's 0 minus 30.7 joules. So there's your answer. So that's why D is the answer for this one. Try to keep the first ones simple. I get the main points across. Okay. How about number 2? What's the kinetic energy of a 1.56 kilogram object moving at 94 kilometers per hour? So we're given mass is 1.56 kilograms. And the velocity is 94 kilometers per hour. All right, so we want to know the kinetic energy. So the formula that operates here is kinetic energy equals 1/2 mass times velocity squared. But if we're going to report the value in joules or kilojoules in this case, you need SI units for all of the measurements. Kilograms, that's mass. The standard for mass is kilograms. How about velocity? What's the standard for time? Seconds, not hours. What's the standard for length? Meters, not kilometers. So we need to convert this one to meters per second. So for hours, bottom, top, we need seconds, right? If you don't know that, then you can convert to hours, minutes, and then minutes, seconds. But I already know 3,600 seconds in an hour. Okay. So that gets rid of hours and leaves us with seconds. Then we want to convert kilometers to meters. So that's 1,000 meters for 1 kilometer. Okay. So now, do a little number crunching. 94 divided by 3600 times 1000 is 26.111. 26.111 meters per second. Now we can plug those in as soon as I figure who just popped in. Ah, Jordan. Okay. There we go. Right, so now we can plug it in the formula. Kinetic energy equals 1/2 times mass times velocity squared. There we go. Now we just need to crunch the numbers. 1.56 to divide 26.11 squared. There it is. Times that. So I get 531.75. If I did that right. 531.75 joules. We look at our answers, and they're all in kilojoules. So we have to find one that matches kilojoules. So if we got this many joules, how many kilojoules is that? Kilojoule is 1,000 joules. So we're going to move this to the left. 1, 2, 3. Okay. I probably should round it off. 3 significant figures here, 3 there, 0.532 kilojoules. There we go. Oh, and then not only that, it's in scientific notation. So this would be 5.32 times 10 to the minus 1 kilojoules, which makes it A. There we go. Okay, this also brings up the point of conversion. If you ever have occasion to solve a problem where you don't have units of measure that cancel, but you know the answer needs to be a particular unit of measure, then you need to know the equivalence. 1 joule is a kilogram meters squared per second squared. That's meters squared per second squared times kilogram. So this is also equal to a joule. That is equal to a joule. Here we go. Okay, that was number 2. Let's see. I better start marking these off. I got number 3 also. Let's see what number 3 has to say. Which of the following statements correctly describes the sign of Q and W for the following exothermic process at 1 atmosphere pressure, 370 K, water gas goes to water liquid? Okay. Gave us a clue already. Said it was exothermic, which is true. If you're going from a gas to a liquid, the system has to give up heat. So exothermic means the Q is negative. All right. Heat has to leave the system in order for it to condense from gas to a liquid. What about work? Let's see. Okay, here, this requires some interpretation. Imagine a cylinder and you got gas in here, and it's under a certain pressure that's constant. What happens when that gas condenses? Creates a vacuum in here, doesn't it? Right? It goes from gas, lots of space, down to a liquid, very little space. So that piston is going to drop, which means the system, work is being done on the system. So that means W is positive. Right? That took a little sleight of mind in order to figure that one out. Now, if this were a rigid vessel and nothing moved, then you would create a vacuum in there, right? But there would be no work done because nothing moves, right? Remember, work, force applied through a distance. Maybe I should read the question. Is it correctly signed? All right. That question should be modified to describe it in a cylinder with a piston. That would be fair. This way, you don't know. Okay, number 4. Yeah, I got 4 marked off also. All right. Oops, too far. For a particular process, for a particular process, Q is 20 kilojoules. And W is 15 kilojoules. So since there's no sign in front of them, we have to assume that they're both positive. Right? Which of the following statements is true? Well, let's look at the information first and say, what does it mean? If Q is positive, that means heat flows into the system. Heat flows in. And W positive means work done on the system. Work on the system. Okay. What else can we say? Well, we have Q and W. We could say, how about the internal energy? Right? The internal energy is Q plus W, which means both of them are positive. So the internal energy of the system also increases. All right. So now let's look at the heat flows from the system to the surroundings. Nope, that's false. It goes the other way. System does work on the surroundings. Nope, it would be negative if that were true. Delta E equals 35. We didn't do that calculation. 20 plus 15 equals 35. Yeah. Right, so that one is true. C is true. All the above are true? No. None of the above? No. C has to be the answer. It's the only possibility. All right. I got 5 marked off also. Which of the following statements is correct? The internal energy of a system increases when more work is done by the system than heat was flowing out of the system. Okay, so now we're going to have to make a comparison. We're talking about internal energy. And that's equal to Q plus W. Okay. So, in scenario A, internal energy of the system increases, right, positive. When more work is done by the system, work done by the system is negative than heat flowing into the system. That's false. If this is greater than that, that has to be negative. Okay, let's see if we got another one. Let's see. 1, 2, 3, 4, 5, 6. That's everybody. All right. So A is false. Can't be. B, the internal energy of the system decreases. All right. So they're saying that it decreases when work is done on the system and heat is flowing into the system. That can't be. You can't add plus and plus and get a minus. So B is false. All right, how about C? The system does work on the surroundings. When an ideal gas expands against a constant external pressure. Yes, if a gas is expanding, goes from here to here, against a constant P, then the gas is doing work on the surroundings. That's a definition. All statements true, all statements false, D and E can't be true. C is the only one that matters. That's the only one that is true. All right, that was 5. Let me look at the next page and see what I got marked. Let's go to 7. There we go. All right. One mole of an ideal gas is expanded from a volume of 1 liter. So initial volume equals 1 liter. Anticipate a final volume to a volume of 8.93 liters. 8.93 liters against a constant pressure of 1 atmosphere. So pressure equals 1 atmosphere. Okay. How much work is performed on the surroundings? Well, first of all, is that true? It goes from 1 liter to 8.93 liters against a constant pressure. Yep. It's doing work on the surroundings. That's true. How much work in joules? All right. So what's the formula? Work equals negative pressure change volume. Right? So what's the change in volume? The change is always the final minus the initial. So work is negative 1 atmosphere. Final volume 8.93 minus 1.00 liters. Right? So that's 7.93, 1 from 8.93, times 1 is negative 7.93 liter atmospheres. Okay? That's how much work is done. But that wasn't the question, was it? It wants to know how many joules. So what we need is a conversion factor. Right? Convert liter atmospheres to joules. So that's why this conversion factor is given as 101.3 joules per liter atmosphere. .3 joules for every liter atmosphere. There we go. So we need to multiply that times 101.3. Negative 803, rounded off, yeah, negative 803 joules. And it looks like B is the answer. Oops, B. There we go. Okay, let's see, I'm still on screen. That's good. All right, so I got that one. Now I want to skip down to number 9. A fuel-air mixture is placed in a cylinder fitted with a piston. Okay. The original volume is 0.310 liters. When the mixture is ignited, gases are produced and 935 joules of energy is released. What volume will the gas expand against a constant pressure of 635 millimeters of mercury if all the energy released is converted to work to push the piston? All right, let's see, what are we given? Well, let's see, we got a piston in a cylinder, and it's 0.310 liters. The initial volume is 0.310 liters. And then it's going to expand to a final volume. We don't know. But we do know it's under a constant pressure of 635 millimeters of mercury. Okay. What else are we given? 935 joules of energy is released. So the change in energy is negative 935 joules. Right? Change in internal energy. All right. We may not need the negative sign. Let's see what happens. Okay, so this looked to me like it's just sort of the other side of the coin from number 7 that we just did. This many joules can be converted into liter atmospheres, right? And then we can convert that, we can set that equal to work. Right? So if we change this to liter atmospheres, we have to divide by 101.3 joules. Okay? So I get 9.23. All right. Oh, sorry. Wrong units. There we go. So now this is also equal to work, which is equal to negative P delta V. Okay, so minus 9.23 liter atmospheres is equal to this value. We know the pressure, 635 millimeters of mercury, but that has to be in atmospheres. Right? So how many atmospheres is that? 760 equals 0.8355. All right, now we can fill in some numbers here. Pressure, 0.8355 atmospheres. And volume is final volume minus the initial volume, which is 0.310. So now we have an equation in one unknown we can solve for. All right, so we'll take this one, divide both sides by that number. Let's see. Yeah, still in there. And that's 11.05. The negative cancels each other. So now we got positive is equal to this one minus this one. Okay. So add this to both sides, right? That's a negative. So we add it to both sides. Three significant figures, 11.4. 11.4 liters, which is C, right there. All right, that was 9. Take a look at 10. Which statement is true of a process in which 1 mole of gas is expanded from A to B? So we got 1 mole of gas and expanded from state A to state B. All right, let's see if the questions add any illumination to this. When the gas expands from state A to B, the surroundings are doing work on the system. Is that true? As the gas expands, it does work on its surroundings. So A is false. The amount of work done in the process must be the same regardless of the path. What type of function is work? Is it a state function or a path function? Work is a path function. The path does matter, so B is false. C, is it not possible, it is not possible to have more than one path for a change of state? False. It's possible to have many paths between two states. C is false. D, the final volume of the gas will depend on the path taken. Does that matter? No. No, the change in volume is a state function. It only matters the beginning and the end. Doesn't matter how you get there. The final volume of the gas will be the same. So D is false. That only leaves E. So E must be true. the amount of heat released in the process will depend on the path taken. Yes. Even if the amount of energy or the amount of heat released is 0, it still depends on the path. All right, so E is the answer to 10. It's the only one that satisfies all conditions. Okay, let's see. I've got 13 marked. As I scroll past 11 and 12, I want to be sure that they're that's simple. 11 is just, it's in liter atmospheres is the answer. So the work done is just minus P times delta V. Calculate the work associated with the compression of a gas at a constant pressure. All right, same thing. Use the work equals minus P times delta V, change in volume. Now we can go to 13. According to the first law of thermodynamics, the energy of the universe is constant. Yeah, that's true. That's one way of stating it. Let's see, we're on 13. Get this fixed. Right. Change in energy of the universe is 0. And that is the whole universe. I mean, that's everything. We haven't confined our discussion to any part of the universe. That's the whole universe. Does this mean that delta E is always equal to 0? Well, since delta E in this case doesn't have a subscript, then no, it doesn't always mean that delta E is equal to 0. So that was a misleading statement. According to the first law of thermodynamics, that one is equal to 0. But if you take this away, that can be anything. Depends on the conditions. It depends on what you define as your system and the surroundings. And is it isolated? Is it open system? Is it a closed system? That makes a difference. So, does this mean delta E is always equal to 0? No. So when the one says yes, that was out. The rest of them say no. So we have to look at the rest of the statement. B, delta E does not always equal to 0, but this is only due to factors like friction and heat. Really? What is delta E? If you're talking about the internal energy of the system, delta E is Q plus W. And they can be any signs, positive, negative, either one. So it doesn't say anything about whether it's friction. It says about heat, but work, friction and heat are related. Work is what's done after you get past the unbalanced force. So B is false. There's more to it than that, not just friction and heat. C, no, delta E does not always equal to 0 because it refers to the system's internal energy, which is affected by that little t. That should be a capital T right there. Right. I don't know if I can change that here. Can I change it here? Yeah, I can change it here. There we go. I better save it if I'm going to change it, huh? There we go. So delta E does not always equal 0 because it refers to the system's internal energy. That's true, which is affected by temperature and work. So there's the work. there's the temperature. Remember, heat transfers only if there is a difference in temperature. That's why temperature makes this statement true. We basically stop there. We could look at the others and see why they're wrong. Delta E never equals 0 because work is always being, no, delta E can equal 0. All right, so that takes care of D and E. When it says never equals 0, they're wrong, right? At the very beginning. There's no argument there. Okay, so C was the correct answer for 13. Let's see here. 14, 15, 16, and 17. Those are good taken together. Okay, we'll get them all on one page. All right. What is true about the value of Q? W, delta E, delta H. So this is for Q. This is W. This is delta E. And this is delta H. Okay. First of all, before we start looking at the trees, let's check out the forest. Is that a state or a path function? It's a path. Work is a path. Delta E is a state. And delta H is a state. Functions. Okay. That may help us answer the questions. All right. 14. Is A true? It is greater than 0. It can be, but you can't just say it is greater than 0. Oh, pardon me. Haha. I missed a step. Consider a gas in a 1 liter bulb at standard temperature and pressure. Okay. Since the temperature doesn't seem to be changing, STP, that's it really doesn't matter. It's connected to a bulb that is a vacuum, right? So we got a bulb here and a valve. There. This is a vacuum. And this is our gas. Okay. Now we're going to open the valve and make some statements about these values. What's true about the value of Q? Right? What happens to Q? Well, we have to assume that this is an isolated system. There's no heat transfer. So when you expand a gas into a vacuum, okay, if that's at standard temperature and pressure and stays at standard temperature and pressure, there's no heat transfer. No, that can't be. Temperature is going to change internally, but there's no transfer of Q across boundaries. Right? So Q is 0. How about work? Was any work done? The gas expanded, but it didn't push against any constant pressure. Right? It just expanded into the space. There's no work done at all. You've just wasted all that compressed gas. No work, equal to 0. What's true about delta E? Well, we have to say that if Q is 0 and W is 0, then delta E has to be 0. If you add two zeros together, you get a 0. How about the value of H? Well, if the delta H is a state function, so has there been any heat movement here? Well, we said there's no heat movement up here. Doesn't matter what the path is. Delta H has to also be 0. So in each one of these cases, nothing has changed. All the values are 0. All right. Okay. Skip 18, go to 19. Which of the following properties are intensive properties? (19) So we got mass, temperature, volume, concentration, and energy. First of all, what is an intensive property? An intensive property is one that does not change with the amount of material, the amount of matter. Right? So one, and what do you have if you do have a change in amount? You have a, well, they say an extensive property. I call it a capacitive property. So this one's not intensive. So if you have more mass, you've changed that value. Temperature. Temperature, as long as the object is equilibrated, the temperature, no matter where you look, and no matter how much you have, is always the same. That is an intensive property. How about volume? If you have more of something and nothing else changes, then you're going to have more volume of it also. So that's an extensive property or capacity property. How about concentration? If you designate or determine a concentration for something like a 1 molar solution, if you have a liter of it versus 10 liters of it, it's the same concentration. So that one is intensive. How about energy? If you have an object at a given temperature and you increase the volume of that object and the temperature with it, then you have effectively increased the amount of energy contained in that object. So energy is an extensive property too, or a capacity property. So these are the only two. Roman numeral 2 and 4 are the intensive properties out of that group. All right, let's see. Do I want to skip to something? Oh, yeah. Let's go to 23. 23. Go. How about this reaction? C2H5OH is ethanol, right? The drinking kind. Combine it with oxygen, set it on fire, right? You got a combustion. And if the combustion is complete, you will get carbon dioxide and water. And this is a balanced equation, right? Just check it out. There's 1 oxygen and there's 6, so there should be 7 oxygens. 4 plus 3 is 7. Yep. You can do the same thing with the carbon and the hydrogens. The enthalpy for this reaction is minus 1.37 times 10 to the third kilojoules, or 1,370 kilojoules. It's exothermic, right? We know because that's a negative sign. Now, consider the following. What are these propositions? The reaction is endothermic. No, it's a negative sign for enthalpy. It's Roman numeral 2. It's exothermic. What else? How about number 3? The enthalpy term would be different if the water formed was gaseous. Is that true? Yes, it would be true. There is a change in heat transfers required for a change of liquid to gas. So yes, the enthalpy would be different if water were a gas instead of a liquid for this reaction. So the state is extremely important. So 2 and 3 are true. So that means E is the correct answer. All right, let's, how about number 24? How much heat is required to raise the temperature of a 5.75 gram sample of iron with that specific heat from 25 to 79.8? Okay, so what's the formula? Let's see, 24. Q, which is an actual measurement of heat transferred, is the specific heat of the material times the mass times a change in temperature. Right? So this is a simple calculation. You say Q equals, specific heat is 0.450 joules per gram degree centigrade. I'm going to put all the units in this one just because it's the right thing to do. And then the mass is 5.75 grams. And the mass has to match the specific heat. Right? Specific heat is in terms of grams. So this is correct at that number of grams. Now the grams cancel. That's good. Now we need a change in temperature. So the change in temperature is the final temperature minus the initial temperature. The final is 79.8. And the initial is 25. And temperature cancels. And leaves us with joules. So by dimensional analysis, we know that we've accounted for all of our units. So we need 79.8 minus 25. So that's 54.8 degrees Celsius times 5.75 grams, and then times 0.45 joules per gram degree Celsius. So I get, let's see, here, 3 units there, 3 significant figures, 3 significant figures there. Yeah. So rounded off is 142 joules. That's positive, that's positive, that's positive. So this is the amount of heat required to raise the temperature. In other words, if the sample of iron is the system, you've got to add that much energy to make the temperature increase from there to there. So that's why the answer is E. Okay. 25. $25. Two metals of equal mass but different heat capacities are subjected to the same amount of heat. All right. You have different heat capacities. So what does heat capacity mean? It means how much will the temperature change if you change the amount of heat added to a given mass. Right? That's why it's, joules per degree gram, per gram degree Celsius. It takes this many joules to make a gram of substance change its temperature by that much. So what does that mean? If these are different, and say, let's see, does it say which one's bigger? Which undergoes the smallest change in temperature? The metal with the higher heat capacity will experience the smaller change in temperature. A higher heat capacity means for the same amount of joules, right? If this is bigger than that one, and this one, J2, actually, they're both the same, J and J. Gram, degree centigrade. No, this is different. It undergoes this many, it takes that much heat to make the grams go bigger. If the grams are constant, if you have the same, if that doesn't change, then the only thing that changes is the difference between joules and temperature. So if this one is bigger than that one, then that means this term divided by that term is greater. Actually, it's not the grams that I want to look at. I want to look at this one. Joules per degree. So that means that for the same amount of temperature, in order to make this one bigger, the denominator has to be smaller. A smaller change in temperature will give you the larger specific heat. Does that make any sense? I like to think of examples. The specific heat of water is 4.18. Yeah, there it is on the next problem, 4.18. Right? And iron is about 0.45. So if you heat iron and water with the same amount of heat, how much will the temperature change? The temperature for iron will change about 10 times as much as the temperature for water. So water has the higher heat capacity. Okay. That was 25. 26. Let's see how I'm doing on time. 3. I got about 45 minutes. Okay. 26. A 32.5 gram piece of aluminum with that specific heat capacity is heated to 82.4 degrees and dropped into a calorimeter containing water with a specific heat of 4.18. Initially at 22.3 degrees. The final temperature of the water is 24.2. calculate the mass of water in the calorimeter. All right. So, I've said before, and I'll say it again, a calorimeter is an isolated system. What happens in Vegas stays in Vegas. Whatever happens in that calorimeter doesn't cross the boundary. No mass, no heat crosses the boundary. So everything that happens in the calorimeter has to add up to zero. Right? You can't create something from nothing. So inside the calorimeter, we've got that. Now we've got two objects in there. We've got water and we've got aluminum. And the heat from either one, both of them together have to add up to zero. So the heat from water plus the heat from the aluminum has to be zero. Okay? Now, the heat from the water is Sm delta T, and the aluminum is Sm delta T. Okay? And they're going to be different, right? This is a different for water, different for aluminum, different masses, and different changes in temperature. Okay? But I noticed there's one thing wrong here. The molar heat capacity is given for aluminum, whereas the specific heat capacity in terms of mass is given for water. Aluminum is 32.5 grams, but we've got a molar heat capacity. So I think the simplest solution for that is change the grams of aluminum to moles. Then you can use 24.03 joules per degrees Celsius moles. All right, so let's change the grams of aluminum to moles. I have to look it up. 27, yeah, 27.0. Rounded off. 27.00. All right, so let's divide that into 32.5. 1.204. Okay, now we've got all the units converted the way we need them. So let's fill out this table. All right, I'm going to give myself plenty of room. 0 equals. So the specific heat capacity of water is 4.18, right? Joules per gram degrees Celsius. How about the mass of water? We don't know that, do we? That's the question. So the mass of water is our unknown. The change in temperature of water. What was the final temperature of water? 24.2 degrees Celsius, and the initial is 22.3. All right. Now we add that to our aluminum. 24.03 is the molar heat capacity, and we've got this many moles. And a change in temperature. The aluminum started at 82.4 and went down to 24.2. So the final temperature is 24.2. The initial is 82.4. Okay? So now we have an equation in one unknown. We can solve for it. Let's resolve this one right here. 24.2 minus 82.4 is going to give you a negative number. Right? Minus 58.2. times 1.204, and then times 24.03. Right? So this term is negative 1684 joules. How about this one? Well, this term right here is 1.9. And then times this one is 7.942. So 7.942 times the mass of water minus 1684 is equal to 0. All right. So now we have to say, all right, add this much to both sides. So that puts this one over here with a positive sign. (7.942) times mass of water. Then the mass of water is this one divided by that one. (212 grams). Okay, so that's why the answer is A. That seems like a lot of work. It took longer than it would. I mean, if I were working it and not having to explain it, I could do it in maybe 7 or 8 minutes. But I just wanted to be clear about everything that has to be done. This is the meat of the problem right here. Then you expand it. You find out that your specific heat is not specific, it's molar heat capacity. And you've got grams, so that requires a change. Right? That's one point that could trip you up right there. Then the rest of it, one possibility is getting your final and initial temperatures in the correct order. Right? Because that gives us a negative over here. If you end up with a negative answer, then you probably switch these around. Okay, that was 26. Let's see, about 29. There we go. Okay, 29. The enthalpy of fusion of ice. Yeah, 29. Okay. I guess it would be written like that. Enthalpy of fusion of ice is 6.020 kilojoules per mole. Okay. When we talk about fusion and vaporization, during those processes, the temperature does not change. So this happens at 0 degrees centigrade. The enthalpy of fusion of ice happens at the freezing point of water. Temperature doesn't change. And as long as you've got ice and water together, this process will continue, either freezing or melting, one or the other, doesn't matter. So when you decide what sign to put in front of it, the enthalpy of fusion, if energy is going into the water to melt it, the sign would be positive. If energy is being released as the water freezes, the sign would be negative. Okay, so if you need a sign in front of that number, then that's the way you interpret it. Okay, the heat capacity of liquid water is 75.4 joules per mole degree C. So the heat capacity of water, liquid water, 75.4 joules per mole degree C. Now, in that case, it's all water, all liquid water, and the temperature does change. Okay. What is the smallest number of ice cubes at 0 degrees, each containing 1 mole of water, necessary to cool 500 grams of liquid water that starts at 0 degrees, that starts at 20, down to 0 degrees? Okay. There are two approaches to this one. You could determine how much energy is required to accomplish how much energy is required to cool 500 grams of water from 20 to 0, and then take that energy and apply it to the rest of the problem. But I would prefer, if I can, to put this all in one formula. If we put all right, if we were to combine water at 0 degrees, and we don't know how much there is of it, and then we combine also 500 grams of water that goes from 20 to 0 degrees, and put those in the same equation, that 0 equals equation, then I think we can answer our question. So inside our isolated system, we have heat transfer from liquid water. I'll just say that, liquid water. And then that is also in there with the Q for fusion. Right? And both of those together have to equal 0. So what does this term mean? This is the one that requires a specific heat. Right? So we need the specific heat of water. Actually, we don't have the specific heat. We have the molar heat capacity. So we have 75.4 joules per mole degree C. Then we have a mass of water, 500 grams. All right, we have to convert that to moles. So 500 grams divided by 18.02 grams per mole will tell us how many moles of water we have. Uh, 27.75. So that goes over here. It cancels that one. And then we have a change in temperature, right? Temperature, final temperature is 0, initial temperature is 20. So final minus initial. So that's the amount of heat that's absorbed by the liquid water. Oh, excuse me. No, it's cooled from 20 to 0. Goes from 20 to 0. So that's let me read that again. Necessary to cool 500 grams of liquid water, initially at 20 to 0. Yeah, okay, that's right. So now we need the Q of fusion. So the heat of fusion is not 3 terms, it only needs 2 terms because there's no temperature change. So the heat of fusion of water is 6.020 kilojoules, and we need to change that to joules because the heat capacity, the enthalpy of fusion is in joules per mole, and this is in joules. Right? And we have to compare apples and apples, not apples and oranges. So this term right here is going to be 6,020 joules per mole. 6,020 joules per mole. And then the unknown is how many moles, what is the smallest number of ice cubes at 0? This is at 0 degrees. So how much energy is being extracted in order to freeze that much water? But we don't know how much yet. How many moles? What is the smallest number of ice cubes? 1 mole each, right? So if we know the number of moles, we know the number of cubes. And this is our unknown number of moles. All right. So let's take this one. Let's take, that's minus 20. And then 27.75 times that, and 75.4 times that. It's a negative 41,847. So I'm going to bring this term to the other side. And it's negative here, so it'll be positive on this side. 41,847 joules equals 6020 X. So X is this one divided by that one. Uh, 6.95 moles. So when it says what's the smallest number of ice cubes, 0.95 is only partial, right? So that's not a whole ice cube. So 6 is the best answer, right? You can make 6, but you can't make 7. You don't have enough. You don't have enough energy for that. So that's why B is the answer. All right. I hope I didn't confuse you too much, but when you put it in this type of reasoning, I find I'm less likely to make a mistake. It's not the only way to work the problem, right? You could do this calculation separate from that calculation and then set the energies equal to one another and solve for the unknown and get the same answer. All right. Let's see, 31. Let me see, how am I doing? Yeah, that's okay. 31. Besides, if we run over, I'll just keep talking and you can watch the video later. Okay, let's make some room. All right. What did I say? 31? Yep, 31. Consider this reaction. Hydrogen plus a half a molecule of oxygen yields water, and the delta H is minus 286 kilojoules. What does that remind you of? Under standard conditions, this is the heat of formation for water. Notice that on this side of the arrow is the molecule with 1 mole only. And the left-hand side, the reactants, have to be modified with whatever coefficient necessary to deliver 1 molecule of water. That's why the fractional coefficient. And this is the amount of energy that is released, right? Negative, it's exothermic. The amount of energy released when these two elements come together. And this is the standard state of hydrogen and oxygen. They're both gases. And the product is liquid under standard conditions. Okay, now let's go back. Which of the following is true? The reaction is exothermic. Yeah, that's true. Yeah, that's exothermic, negative value. Can't be endothermic too. How about C? The enthalpy of the products is less than that of the reactants. Is that true? Look at it this way. Oops, that's oxygen. Okay, and you make water. All right, if the enthalpy is negative, where would that put it in this formula as a component, a reactant, or a product? If it's exothermic, it's a product. All right, we're releasing that heat. So what does that mean in terms of the heat content, the energy content of the reactants versus the products? That energy used to be in here. Now it's out there. So that means the enthalpy of this compound is less than the combined enthalpy of these reactants. So C is true. The enthalpy of the products is less than that of the reactants. So A and C are both true, which makes E correct. How about D? Heat is absorbed by the system? No. Heat is released by the system because it's exothermic. So E is the answer. A and C are both true. All righty, let's move on to 35. There we go. 35. Let's see, did I miss anybody? 1, 2, 3, 4, 5, 6. No, we're good. 35. All right. If 5 kilojoules of energy is added to a 15.5 gram sample of water at 10 degrees Celsius, the water is what? Boiling, completely vaporized, frozen solid, decomposed, still a liquid. All right. So let's look at it this way. That much energy is added to a 15.5 gram sample of water at 10 degrees. Is the temperature going to go up or down? It's going to go up. Now the question is it boiling, completely vaporized? It's not decomposed, right? There's not enough energy for that. Is it still a liquid? It's not frozen because the temperature's going the wrong direction. So it's either still a liquid or it's boiling, in which case you would have vapor and liquid, or it's completely vaporized. You've added enough energy to completely convert all of that water into gas, right? So it's either A, B, or E. So how do we tell? We say the amount of energy, the heat added to it is 5 kilojoules. 5,000 joules. So Q equals 5,000 joules. And the mass is 15.5 grams. And the sample temperature starts at 10 degrees. The initial temperature is 10 degrees Celsius. So we need to find out what the final temperature is. So all we have to do is set this equal to Sm delta T. So that means 5,000 joules equals 4.18, right, for water, specific heat capacity. Mass is 15.5 grams. And final temperature minus initial temperature. Okay. So we just need to find out what the final temperature is. If the final temperature is right at 100 degrees, then you will have, well, not necessarily. Let's just find out what the value is first, and then I can talk about it. So this term right here, these two together, is 64.79. So that, since that's a multiply, we can divide this, both sides, into that. And that's 77.17. 77.17 equals final minus 10. So the final temperature is equal to 10 plus 77.17. 87.2. All right. So if it's 87.2 degrees Celsius, is the water boiling? No. It's not boiling. It can't be completely vaporized because it hadn't even reached 100 degrees yet. So it's still a liquid. It's just a hotter liquid. Right? So that's why E is the answer. Okay? All right, that was 35. Let's see, what do I have marked next? Ooh, I skip a lot. Must be a lot of repetition. Or maybe I didn't mark all of them. I got 55 marked. We could do that one. 59 is similar to that one. $65 is a good one. 70, yeah. All right, let's come back to we'll come back to 55, 59, maybe 65. I want to get, before we run out of time, I want to move to the end. Fill in the blanks and yeah, fill in the blanks. We'll get those out of the way and then we'll come back. Let's see, they started about 84. There we go. All right. These are really simple, but I did want to get them out of the way. Consider this following reaction. 2 aluminums, 3 chlorines makes aluminum chloride, and the enthalpy is minus 1390.81 kilojoules. Is the reaction exothermic or endothermic? Well, obviously it's exothermic because the value is negative. How much heat is produced or required when 10 grams of aluminum chloride forms? Right. So 84 is based upon this reaction. Two AlCl3. And for this reaction, the enthalpy is minus 1390.81. Kilojoules. Now, that kilojoules is for this balanced equation only. And you interpret it based upon the coefficients. So this will be that many kilojoules for every 2 moles of product, or half of that per mole of product. All right, how much heat is produced or required when 10 grams of aluminum chloride is formed? Right. So if we got 10 grams, 10.0 grams, how many moles is that? Because this is all based in moles. So we need 10 grams converted to moles. We looked up aluminum earlier as 27.00. So 10 divided by 27 is 0.3704 moles. Okay? So now we know that interpreting this correctly means that the total amount of energy is equal to 0.3704 moles. And this is for every 2 moles of aluminum chloride, minus 1390.81 kilojoules. Right. That's important to put that 2 moles down there. Let's see, 1390.81 times, let's see, 258 minus 258 kilojoules. Is that one of our selections? How much heat is produced required with 10 grams of aluminum? No, I got that wrong. What did I do wrong? Did I get that right? Yeah, 27. 10 divided by 27. Yeah, that's about a third. Maybe I did that calculation wrong. Hold on a second. 0.3704. $258. So, where did I go wrong? How much heat is produced? 10 grams of aluminum chloride are formed. You know, that doesn't look right. Let me see where I went wrong. Oh, duh. Nobody said anything. Rookie error. Aluminum chloride is not 27 grams. 27 plus 3 times 35.45. So that's 133.35. 133.35. 7.499 times 10 to the minus 2. Moles. Now, $52.1. Kilojoules. Right? Close enough. All right. Don't do as I do. Do as I say. All right. How many grams of aluminum are required to absorb or evolve 1 kilojoule of energy? All right. So, this, if we start off with 1 kilojoule of energy, then what converts that to grams of aluminum? Well, it's that many kilojoules, 1390.81, per 2 moles of aluminum. Right? So there we've converted to moles of aluminum. The question is grams. So we need to convert moles to grams. Now that one's right, and it's just aluminum. There we go. So now all we have to do is, that's the thinking part. Uh, 0.0388 grams of aluminum will release 1 kilojoule of energy. All right. Now let's see how many more I can mess up. Okay. 85. Using these two equations, N2 plus 2O2 yields 2NO2 requires 67.7 kilojoules. That means that you have to put in that much energy. Similarly, N2 plus 2O2 yields N2O4. That requires 9.7 kilojoules. These are both endothermic reactions. The question is, how much energy is involved in the reaction 2NO2 yields N2O4? Right? With the sign. Let's see. So what we've got here is an example of Hess's law, where we're combining reactions to get this target reaction. So we've got N2 plus 2O2 yields what?
2NO2.
And the 67.7 kilojoules.
That's the delta H.
All right. Now we've got
N2, I'm going to give myself a little bit of space,
plus
2O2
yields
N2O4.
Okay, and that requires
9.7 kilojoules.
Okay, what's the target reaction? 2NO2 yields N2O4.
2NO2 yields N2O4. And we want to know
what's the delta H for that. So we've got N2O4 on this side. That one's good, just like it is. But we need
NO2 on this side. Those two NO2s need to be over on this side. So this goes 2NO2 yields N2 plus 2O2. And this one changes sign. All right. So if we combine these two, do we get this reaction? Right? Here's one. There. 2NO2. That's good. There, there. That one cancels that one. That one cancels that one. We're good. All we have to do now is add these two together.
Right, that's a negative, and then a 9.7 is minus 58. Okay? So that was a really simple one, illustrating Hess's law. So we can answer the question also, is it exothermic? Yeah, it is. It's pretty good size exothermic. This one is also a Hess's law, but it would take a lot of work to get there. All you have to do is be sure that when you add up, once you've manipulated these equations to get the reactants and products on the right side and then the right amounts, when you add them together, do you get this final equation? And if so, then the values that you've accumulated here for the delta H's of each of these that go into the final, add them together. Incorporating the signs, keeping track of the signs also. And that's why you would get that value. I've worked this problem before with other classes, and it takes a while. So considering the fact that we don't have much time, if you need details, then go to the review document, worked problems.
But this one illustrates the use of Hess's law.
All right. So let me see what else, what other trouble I can get into. Let's see. See if I've marked off any of those. I think I'm out of time, aren't I? 3:45. I'll see if there's any in here that are, okay, let me work my way back. Oh, I know one. Yeah, I know one that I do want to do. Yeah, 65. Go back to 65. You can hang around if you want to. If not, I'll keep working the ones that I think are important. Let's see, let's do this quicker. 65. There we go. All right. So we want to use this information these two reactions and Hess's law to determine the standard enthalpy of formation of copper 2 oxide. All right? So you have to know how to write the standard enthalpy of formation equation for copper 2 oxide. 65. I'm going to put it down here because that's our target equation. So if we're going to have copper 2 oxide, solid, that's how you start your standard enthalpy of formation. You start with the product, 1 mole of it, and then you work backwards to oxygen 2 gas. That's the standard form for oxygen, and copper, like that. Then you balance it. We need 1 copper, 1 copper. We need 1 oxygen, so there's a half here. That's our target equation. Excuse me. And we're going to use these other 2 equations, see if we can determine the standard enthalpy of formation based on the information that's given in these 2 equations right here. So Cu2O, solid plus 1/2 oxygen gas yields CuO. CuO. And that enthalpy is minus 144 kilojoules. Okay, how about this one? Cu2O yields copper solid and copper 1 oxide. Yep. And that enthalpy is, this is standard enthalpies, is plus 11 kilojoules. Okay. So now we need copper oxide on the right-hand side, only 1 of them. So we've got 2 here and we've got 1 there. So if we put this one on that side, that would cancel 1 of them. Let's see if that gets us anywhere. That also puts copper on this side, which we need. And it puts copper 1 oxide on that side, which will cancel this one. So I think that's what we need to do. We need to flip this one over and make this one copper plus copper oxide yields copper 1 oxide solid. And that would make this negative 11 kilojoules. Okay. So that takes care of that. There's our oxygen here. I think we're good to check it out. So we're going to use this one and this one. That means this one and this one. Okay. Copper. Copper, copper. 1/2 oxygen. 1/2 oxygen. Copper oxide. 2 copper oxides, but 1 cancels. Right? So we'll cancel that one, 1 of those, and that one, which leaves us this one and those 2 together. And this one and that one cancel. So that covers those. That covers those. There, there. We're good. So now we can add these up. Those right there. So it's negative 155 kilojoules. 65. Negative 155. There you go. E. Notice that there's a plus in here, right? So if you don't set it up right, you could end up with the right number but the wrong sign. And of course, that's wrong. All right, let's see. Let me back up some more and see if there's anything else that needs to be handled.
there's another Hess's law here with phosphorus. Takes a little more work. This one shouldn't take too long, number 55. Although, you know, it's A, B, C's, and D's. But maybe we can live through it. All right, so let's try this one, and that should finish out the day. All right, we're given for 55, we're given 3 B's equals 2 C's plus a D. 3 B's, equals, yields, 2 C's plus a D, and that's minus 125 kilojoules per mole. The next one is 1/2 A yields B plus 150. And then E plus A yields D. E plus A yields D for plus 350. Okay. The target equation is B yields E plus 2C. And we want to find the enthalpy. All right, let's look at this. Where are the B's? There's a B, and there are 3 B's. Right? If we added these two together now, we'd get 2 B's, and we can't have that. We only need 1 B. So let's keep that in mind and look at the others. We need an E on this side, so this one has to be flipped. We know that. So let's go ahead and change that one. And that makes this one a minus 350. Okay, so we're going to use this one here. That gets that one and that one. And how about C's? 2 C's on this side. Okay. Yeah, 2 C's. That's good. Right? So we'll leave that one alone. How about this one? A. Well, now we've got an A on this side and a half an A on this side. We want to cancel the A's because there's no A in there. So let's multiply this one by 2. That yields an A, 2B, and 300. So let's take those 3 together and see if that gives us what we want. There's a B. There's 3 B's, but there's 2 B's. So these 2 B's cancel those 2 and leaves us with 1. Okay, B's are covered. How about 2 C's? Right, 2 C's, there we go. 2C, 2C. How about D? That D cancels this D. How about A? There's an A, and there's an A. Right? So, those are gone. These are accounted for, gone. Those are accounted for, gone. We're good. Now we just add up. 350 plus 300 is minus 50, right? Minus 50 and 125 is minus 175. So let's see. Is that the answer? C, minus 175 kilojoules per mole. It takes a little practice to try to figure out what's the next step Some of them are not obvious. But I've run out of time. If you're not real comfortable with using Hess's law,
you should go in and look at some of these examples that we didn't cover today and practice them. There are several of them in there that we didn't hit. So if you practice those, then you can get a feel for working with Hess's law.
all right.
So that's all I have for today.